BERT Explorer. BERT, which stands for Bidirectional Encoder Representations from Transformers, is a revolutionary model in natural language processing, or NLP. Unlike traditional models that read text in one direction, either left to right or right to left, BERT analyzes text bidirectionally, capturing the context from both sides of a word. This bidirectional approach allows BERT to better understand the nuances and semantics of words in a sentence. It's like reading a book and understanding the meaning of a word not only from the words that precede it, but also from the words that follow it. That's the magic of BERT. Its architecture is based on the concept of transformers, which use attention scores to weigh the importance of different words in a sentence. This attention mechanism helps the model focus on words that are more relevant in a given context. BERT's capabilities have led to breakthroughs in several NLP tasks, such as question answering and spam detection. Its ability to understand the context of words in a sentence makes it exceptionally powerful, and its pre-trained models can be fine-tuned for specific tasks, saving time and computational resources. This tool provides a comprehensive visual exploration of the BERT model, a cornerstone in NLP and deep learning. Dive into its architecture, configurations, and intricate workings, all presented interactively for an enhanced learning experience. Let's explore this tool. First, we take a look at the BERT model right here and try to understand how it works. BERT is like a smart machine that understands language. Think of its configuration as its blueprint or settings, detailing how it's built. When you give it some text, BERT first breaks it down using Input Embedding, and that is to convert words into a format it can understand. It then uses positional encoding to remember the order of words because sequence matters in a natural language. Inside of BERT, there is a mechanism called multi-head attention that helps it focus on important parts of the sentence. After paying attention, it uses add and norm to combine and stabilize the information. BERT then processes this information through a feed-forward network to make sense of the information. This whole process happens in multiple layers called encoder layers, each refining and understanding the text. The BERT model is trained using a technique called masked language modeling, or MLM. Here's how it works. Imagine you have two sentences and you hide or mask some of the words, like playing a fill-in-the-blanks game. You then feed these sentences with the missing words into BERT. As the sentences move through the different layers inside BERT, the model tries its best to guess or predict the hidden words. Let's see it as an animation. Here is one of the sentence pairs to train the model. The cat chased the mouse. It was a fast chase. This input text is first masked by replacing the word cat and chase with a special token mask, as shown here. This masked input is then fed into the BERT model and then trained using multiple encoder layers and running multiple iterations or epochs. At the end of the training cycle, the BERT model predicts the masked words as cat and chase. The model also tries to predict if this sentence pair has a logical continuation of a previous sentence pair using the flag isNext. In this BERT Explorer tool, we will explore various components and pieces of BERT so that we can understand what goes on in each step. We will use some predefined training examples to probe the data inside BERT to make presentation easier. We flip the model upside down so the navigation becomes easier, like this. Also, for simplicity, we will use only two encoder layers in our model. We will explain the configuration, input text, input embedding, multi-head attention, add and normalize, feed forward, scaled dot product, and the feed forward networks. and components. Finally, we will explore the output and prediction parts of the system. Here is the configuration of this BERT model. The maximum number of tokens per sample is 14. The number of samples per batch is 6. To make things simple, we use one batch in total. In other words, 6 sentences in all. The number of predictions per sample is 2, which means we will not mask more than 2 words per sample. As mentioned earlier, the number of encoder layers is also 2. The dimension of embedding space is 7. Please note that in real life, this number is much higher, maybe in the hundreds. There are some feed-forward matrices and vectors, which you will see a bit later, and the dimensions of this space is 28. The dimensions of Q, K, and V entities, which are used in the attention score, which is also something you'll see later, is 4. Finally, the number of segments or sentences per training sample is 2. Here is the block of input text containing 1, 2, 3, 4, 5, 6 training samples, each training sample containing 2 sentences separated by a period. Each sample is separated by a new line character. Here, we show how these input samples are masked and standardized as per required by BERT using special tokens like CLS for class, mask for masking, SEP for segment sentence separation, and PAD as padding to make all training samples of equal size. As indicated here, the below diagrams are equipped with clickable image maps that allow you to access and view data elements. For instance, we can explore data blocks in the Input Token section. If we click Input Words, a soft dialog appears showing data as plain text and grid format. Here we see the text, and if we click on the Grid tab, we see the data in grid format. This and other data view formats will be very handy to show more complex data in the BERT model. We can also use these next and previous buttons to navigate through data blocks by going to the next data block or the previous block, like this. Here I'm clicking the next, and then I can go previous back to input words. We can dismiss the dialog by using the X button or clicking outside the dialog. Let's probe some more data blocks. We can click number dict to see all the words used in the training samples along with their numerical values or tokens. These numerical values are the ones which will be understood and interpreted by the model. Because this data is in JSON form, the grid view will not be applicable here. We can see that right here. Let's close this dialog. The next data block is masked tokens. Let's see this data. These are the tokens for the masked words. For example, 37 and 16 are the tokens for the words cat and chase in the first training example. So masked words cat and chase. The isNext dialog tells us if 2 sentence pairs in each sample are logically connected. The way how we predict isNext will be explained a bit later. The input IDs are all inputs converted into tokens, where each row represents a sample pair of sentences. The segment IDs identify each word in a sample as it belongs to the first or second sentence. 0 means the first sentence, and 1 means the second sentence. The masked position shows the position of the masked word in the sample. For instance, in the first sentence, the second and 11th words are masked. Pay attention to the numbers shown within the rectangular blocks. These are the dimensions or shape of the data, like rows and columns for 2D data. Here we can see the input sample, and we can choose one of the 4 input samples to explore the BERT model. By the way, the input sample can also be changed later on while probing the data with pop-up dialogues. For now, I'll choose sample 0. The next section is Input Embedding. These gray circular nodes shown with numbers are connected with each other like this. Number 1 is connected to this, number 2 like this, and so on. Also, these data blocks, input IDs, segment IDs, and masked positions are repeated here. Input IDs, segment IDs, and masked position. However, because the scope of these blocks and later blocks are now limited to one input sample only, the dimension of data is reduced. For example, from 6 by 14 to just 14. Let's view this data. These are the 14 input IDs which belong to sample 0. As mentioned here, all steps from here and below are iterated over epochs, and we can view the data for various epochs to see how training is helping the model to converge to a steady state in a well-trained system. For example, if we want to see various embeddings or number values during training, we click one of these blocks, say token embedded, and now we see some more elements and controls on the data view dialog. We see a drop-down to select input sample. We see next and previous buttons like we mentioned before, and we also see these new next and previous buttons to iterate through well-known epoch numbers. Let's try them by first switching the view mode to grid. Make sure it's on grid. We can also do text, but I'll keep it for grid, and we can start pressing next. So in this grid, the first column shows the words that were selected in this input sample, sample 0. And the remaining columns are components of the embedding vector for each word. Please note the embedding dimension is 7, which was previously set in the configuration section. We can select another input sample, let's say sample 2, and notice that the words and their embedding values are changed. Let's try rotating through the epochs again, and we can click next, so we go to epoch value of 1250, and we can keep pressing next, and the embedding values keep converging to their final state until we reach the last epoch, which is 5000. We can rotate the epochs back to 0. Let's switch the view format back to text and select input sample 0, and I'm going to close the dialog. Similarly, we can view the position embedding using this block here. Segment embedding can be viewed using this block, and the combined embedding can be viewed using this block. This attention mask block shows if any word should be ignored in calculating the attention score. Here, the rows and columns are the same input words, and the value false means don't ignore attention scoring. Next, we have 2 sections showing the encoder layer of the BERT model. As mentioned before, in real systems there are many more encoder layers, but we use 2 here for simplicity. Let's explore what's in each of these encoder layers. The inputs to an encoder layer are embedding vectors, attention mask, and masked position. The output of an encoder is again the embedding vectors and propagation of attention mask and masked position. The major part of an encoder is the MHA, or multi-head attention, which is this light gray box. Within this block, we compute the attention score for each attention head. In this demo, we are using 5 attention heads, as shown here, through H0, H1, H2, H3, and H4. Please note that multi-head attention is a larger topic, but at a high level, it allows BERT to focus on different parts of a sentence simultaneously. It's like reading a book and being able to pay attention to multiple plot lines at once, helping the model capture various aspects and relationships within the text more effectively. In another tool called Attention Heat Map, we have covered how to calculate and view the multi-head attention. Now, back to the encoder data blocks. As attention score requires entities like query, key, and value, everything related with the query is shown here, the key related stuff here, and value related stuff here. Initially, the input embedding becomes the Q, K, and V matrices. As part of the training process, 3 linear weight matrices, WQ, WK, and WV, are applied to the initial embeddings Q, K, and V. That's to generate WQQ, WKK, and WVV. In this tool, when you see a black data block, it will most likely present a training linear weight matrix. We can view these data blocks by clicking on them and analyzing the data by changing input samples and/or rotating through the epochs. These WQQ, WKK, and WVV entities are then split into 5 entities each. This is to introduce 5 heads in the multi-head attention calculation. Please note the data shape changes from 14 by 20 to 14 by 4. These new entities are represented as lowercase qs, ks, and vs. The attention head numbers shown as H0 through H4. Using these entities, the attention score is calculated using this formula for each attention head. Please note the attention mask is also used in the final calculator of the attention score. Let's explore some attention score blocks. So I'll click on attention head 2 and make sure it's on grid format. For attention related stuff, we show the grid data in color coding. The first column and the first row in the grid are the words in the input sample, sample 0. The values at any intersection represent the relationship between the words. These relationships can be things like next word relationship, pay attention relationship, pronouns relationship, etc. Using more attention heads makes the system learn more relationship types. The light color shows higher values and the dark color shows lower values. Let's rotate through the epochs so that the model becomes fully learned. We press this next button until we have reached epoch 5000. By analyzing the numbers and color at the intersection of the words, you can see how the system has learned the relationships. For example, in this input sample, sample 0, and for this particular attention head, which is head 2, we notice a higher value between cat and chase. There are many other types of relationships you can spot by different input samples and different attention heads. Let's go back to the encoder section. The next operation in the encoder is the multiplication of attention score with the value entities VS. This happens for each attention head. This product is called the context of each word, shown as CTX. And CTX, or context, captures the essence of its surrounding information in the sentence. Then we concatenate the context entities for all attention heads into a single entity. This is for easier processing and propagation. A linear weight matrix is then multiplied with the context to get this output. This step brings the entities back to the original embedding dimensions of 14 by 7. We then add the residual of the input embedding to this context output to ensure that the original embedding information isn't lost during a long series of data transformations. After this, we apply layer normalization to generate the final MHA multi-head attention. We apply this step to stabilize and standardize the activations, ensuring that context data don't reach extremely high or low values. Let's see how this MHA entity looks like. So this is the MHA entity, and I'll take it to the EPIC 5000. And we see that each word has an MHA or multi-head attention vector associated with it. Next, we apply another linear weight matrix to the MHA to get an output which is better shaped and optimized for further processing and generating the encoder output. After this, we apply a GALU, a Gaussian error linear unit activation function. This nonlinearity allows BERT to capture and model more complex relationships in the data. Then we apply another linear weight matrix, and this is applied to the output to generate the encoder output. This step transforms the data into a shape which fits the embedding dimension of 14 by 7. This is so that we can feed this into the next encoder layer. The second encoder layer, layer 1, takes 3 inputs just like encoder layer 0, the embedding, the attention mask, and masked position. We can explore this second layer just like we did by the first one through probing various data blocks. I'll click the attention head, H0. I can go through the different epochs, different samples, and it applies to all of these data blocks. As mentioned earlier, we are using only 2 encoder layers, but in real systems, the number of encoders can go up to a couple of dozens or even more. Multiple encoder layers in BERT allow the model to iteratively refine and capture increasingly complex relationships and hierarchies in the input data. With each successive layer, BERT can understand deeper nuances, contexts, and dependencies in the text. Next, we have an output layer, which takes 2 inputs, the output from the last encoder layer and the masked position. In this layer, the data is separated out into 2 zones. On the left-hand side, we process the data for isNext prediction, and on the right-hand side, we process the predicting the masked words or tokens, in other words, for masked language model. Let's explore what masked language model processing is. Let's take a look at the masked position block and make sure sample 0 is selected. We see the numbers 2 and 11, meaning the word index 2 and 11 are masked in the sample 0. We can verify this by going back up to the masked input text section, and we see 0, 1, 2. 2 and 11 are the 2 words that are masked, positions 2 and positions 11. Let's go back to the output section. Next, we can expand this entity by generating 2 rows of data, with the first row being the number 2 repeated 7 times, and the second row being the number 11 repeated 7 times. Remember, 7 is the dimension of our embedding. Using this expanded form of masked position entity, we extract these cells from the encoder output, and this is the input to this layer. In other words, we extract 7 consecutive numbers from row 2 of encoder output and 7 consecutive numbers from its row 11. After this operation, this is what we get. As we just mentioned, these numbers are extracted from this data block, particularly this row and this row. Next, we apply a linear weight matrix to this H masked entity to get this output. This step adds some additional training aspects to the H-masked entity. After this, we apply a GELU activation function to get this output. This step is used because it improves the model's learning capacity by providing nonlinear transformations, which help in capturing complex patterns in the data. After this, we apply layer normalization to stabilize the training process by normalizing the inputs across the features. Next, we apply a special decoder weight matrix to the H-masked entity to reshape and optimize it to the output block. The decoder is applied to transform the H-masked entity into the vocabulary size, allowing the model to predict the likelihood of each word in the vocabulary, thus enabling the prediction of the masked words. Please note that there are 41 words in our vocabulary for this toy BERT model. A bias is added to it to generate the Legits LM, or Legits for Masked Language model. This step is helpful in improving the accuracy of words predictions by providing a bias correction, a typical step in deep learning. These Legits are calculated to represent the raw scores or predictions for each word in the vocabulary before determining the masked word. In general, Legits refer to the raw, unnormalized scores output by a neural network's final layer before applying a normalization function like softmax. These scores represent the model's confidence for each class. In the case of BERT, Legits LM represents the Legits for the masked language model, indicating the model's raw predictions for the masked tokens. Let's see how these Legits look like. Here are the two rows, which are the number of masked words predictions. The columns translate to the word number in the dictionary of all samples. Let's iterate through some epochs to make the model fully learned. So I'll take it to 5,000. And we can notice that the updated Legits as a heat map where each cell represents the raw prediction value. The varying shades of green indicate the magnitude of these values, with brighter shades representing higher values. Please note that the high Legits value for row 1 are in column number or word number 37. And for row 2, a high value of Legits is in column or word number 16. These Legits will undergo further processing, such as applying the softmax function to yield the final predicted probabilities for each word in the dictionary. Let's now explore the isNext processing. We extract the 0th row from the encoder output, which we can see in this block here. Here are the 0th row elements. Extracting the 0th element from the encoder output is crucial for the isNext classification task. This task determines whether one sentence follows another in a coherent manner. The 0th element often represents the special classification token, CLS, that BERT uses to capture the aggregated representation of the entire input sequence. Next, we apply a linear weight matrix to the extracted output, and that produces this output here. This operation helps to refine and rescale the extracted features from the CLS token, enabling better alignment and preparation for the subsequent classification task. Next, we apply the tanh activation function to scale the values between -1 and +1, and we call this entity hPooled, signifying the hidden state to pool or process the isNext classification. Then, we apply a linear weight matrix to it to reshape and optimize the data, and we produce the Legits CLSF, or Legits for classification. In the BERT model, Legits CLSF refers to the classification Legits used to predict whether the second sentence follows the first sentence in the input sequence, which is the isNext classification. These Legits are used in the next sentence prediction, or NSP, task during BERT training. The two classes in play here are NotNext and isNext. let's explore this entity. So we can, again, iterate through this entity, and I'll take us to epoch 5000. And pay attention to the first and second values of legit's entity, which corresponds to the not next and is next classes respectively. For sample 0, is next is negative. For sample 1, is next is also negative. For sample 2, is next is positive. These values will be further processed to generate the true or false values, hopefully matching with input is next labels. Let's go back to the main flow. In the next stage, we will explore the prediction stage for the legits. The legits LM for mask language model, and the legits CLSF for the is next classification. In the final stage, we first explore the masked language model. The softmax activation is applied to legits LM to get the probability distribution over the entire vocabulary of words. So I'll click on output and sample 0. And note that the first predicted masked word with the highest probability is the word number 37, shown with this bright color. The second masked word has the highest probability with word number 16, shown with the bright color again. Let's go back. Now, if we apply argmax to this data, we should get the word index 37 and 16 as an output. Please note that the argmax is a function that selects the index of the maximum value along a specified dimension, in this case, the rows. Let's see the output. Here, the number 37 and 16 are the predicted tokens, or word numbers in the vocabulary. This should match with the actual tokens. If I click actual tokens, and they are 37 and 16. If we go back and look at the number dictionary entity, the word associated with the number 37 is cat, and the word associated with the number 16 is chase. So we can say that the BERT model has correctly predicted the masked words. Now let's quickly explore the is next classification. Remember that legit CLSF are the raw values for the two classes, the not next and is next. Let's look at the values. So for this sample pair, the legits are 3.3 for not next and negative 4.01 for is next. Next, we apply the max operation and create the tensor, which indicates the selected 0th tensor value is 3.30, and it is the 0th index. Next, the index of this higher value tensor is extracted, which means that the not next is true and is next is false. And when we convert to Boolean, we see it here as the predicted value shows false, and the actual value is false as well. To summarize, let's take a look at how BERT predicted the masked words and is next flags for the 4 input samples we used in the training. Here is a table showing the 4 input samples, the predicted and actual words, and is next elements. Please note that BERT has performed all the predictions correctly. This covers a comprehensive visual exploration of the BERT model. Please feel free to play with this tool by going through various input samples and probing data entities at different blocks and stages of the BERT model.